Today we're going to begin to talk about tangent lines. Now tangent lines are a line that just touches the curve. And it actually just touches the curve so that that tangent line and that curve only share one point. In this first picture, that happens about right here. They only share one point. And in the second picture, it shares right here. Well, what we're going to be learning to do today is how to write the equation of the tangent line. Typically, when we write an equation of a tangent line, let's sketch a curve here. Say we want the tangent line right here. So we're trying to write the equation of that line. Typically, when we write an equation of a line, we need a slope and we need a point. Now, we have a point. That point right there, the black one where the line touches the curve, is a point. How do you get slope when you only have one point? Typically, our slope is y2 minus y1 and x2 minus x1. But in this case, we only have one point. How are we going to deal with that? I'll show you. Let's say we estimate another point on the curve, because all we know about is the curve. So let's say we put a point right here. What can you tell me about the slope of the dashed blue line and the solid black line? Nothing alike, right? Those points are far apart, weird things are happening. Let's move a little closer. What do you notice about the slope of the green and the black line? Still not very much alike, but getting better. If we pick one really close, it gets to be a little bit better, almost parallel or on top of that black line. So, ideally, we would want to pick the point, the black point, and the point directly next to it. So, let's look at a specific example so we can talk about this. It says find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. We know the point 1, 1. We need another point close to 1. If I asked you what is the x value closest to 1, you would probably say 1.1. And I would come back with, what about 1.01? And then you would say, what about 1.001? And then I would say, what about 1.001? And we could go on forever because we could always name another point that was closer to 1 than the one the previous person had said. So instead of picking out a specific point, we use the point 1, 1 that we know, and we use a generic point based on the curve. We don't know its x value, so its x value is just x. We don't really know its y value, but we know something about y in this particular situation. Our y is x squared, which means instead of just putting y, we know the relationship between x and y is going to be x and x squared. So, we think about these as 2 points on our curve, one we know and one we don't know, but we're going to make really close. Our slope would be x squared minus 1 divided by x minus 1. Now, grab your calculators because we are going to work some of this out using our graphing calculators. On your graphing calculator, go to your y equals. In it, you're going to put this equation. X squared minus 1 divided by x minus 1. Oh. It's my division. There we go. Now, on your notes, I provided you with a table. I won't always give you the x values. Sometimes you need to think about it and come up with that. The point being, we're approaching 1 from the left when we go from, or from the right when we go to 2 to 1.001. So, approach from the right. These bottom numbers are approaching from the left, so make sure you approach from both, and we're going to hope and see that they are both approaching the same value. So, back at your calculator, we're going to go second graph to our table, and we're going to plug these numbers in. We've got 2, 1.5, 1.1, 1.01, and then there were more approaching it from the left, so plug in all 10 of your numbers. When you do that, you should end up with 3, 2.5, 2.1, 2.01, 2.001. And then when we plug in 0, we get 1, 1.5, 1.9, 1.99, 1.999. You notice, as we look at these values, we're getting closer and closer to 2. Is that the same thing that's happening from the left? 1, 1.5, 1.9. It's also getting closer and closer to 2, which tells us that our slope is probably 2. You don't know much about this notation here, but it says the limit as q approaches p. We'll learn more about limits later this chapter, but what it means as q gets closer and closer to p, which is exactly what we did on this table. We got closer and closer to p from one side, and then closer and closer to p from the other side. So, we know our 2 is our slope. So our slope is 2. We have the point 1, 1, and we can write our equation of our line, whether you use point slope form or slope intercept form, doesn't matter. But we get y equals 2x minus y. Now, pause the video. On the back of this front page is another example that is just like the example I just did with you. Do this before class tomorrow and before we go on to the next example in this video, and tomorrow in class we'll go over it and I'll make sure that you know what you're talking about. Velocity. This can apply to real life. Suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. From physics, we know that distance fallen by any free falling body is proportional to the square of the time it is falling. This distance, denoted as s of t, is measured in meters. At t seconds is expressed as s of t equals 4.9 t squared. Now, instantaneous velocity is one thing. Today we're talking about average velocity. And anytime we're dealing with average velocity, it's the distance traveled over the time elapsed, where when distance is our y and time is our x, means average can be described as slope. When we're finding average velocity, we can do slope of the position graph. For example, s of t equals 4.9 t squared. When I plug 5 into that graph, I get 122.5. Now our second point is our generic point. We don't know where it is. We're going to make it close to 5, but not on top of 5. So we're just going to call it t, and the y is going to be 4.9 t squared, because if I plug t into s of t, I would get 4.9 t squared. It's our generic formula that's on the curve. Now, be careful. As we do these, we're going to be finding slope each time. But these numbers in brackets don't mean the 0.56. It means we want the point at 5 and the point at 6. At 5, it's 122.5, which we found earlier. If you plug 6 into 4.9 t squared, you get 174, 6.4, sorry. Find the slope between those 2 points. You'll find that it is 53.9. Do that again and again. The point at 5, which will always be the same, and the point at 5.1. Plug the 5.1 in to get the y, 127.45. When you find slope of those 2 points at 5 and 5.1, you get 49.49. Do it again using 5 and 5.01, and then again using 5 and 5.001, and you get the following 2 slopes. It appears that as we shorten the time period, the average velocity is getting closer and closer to 49. Now, what's the difference between average velocity and instantaneous? Instantaneous velocity when t is 5 is defined as the limiting value of these average velocities over shorter and shorter periods that start at t equals 5. Average velocity is when we're using 2 points that aren't quite the same. Instantaneous velocity is if we really could find the slope of a line that we only knew 1 point of. We can't do it yet. It is coming a few weeks from now. But because we used our average value to estimate the slope at 5, we're pretty sure that the instantaneous velocity after 5 seconds is 49 meters per second. Eventually, you will be able to know for sure. For now, we're just estimating. So, another look at this. This should be something familiar to you. If we have P and Q, meaning a point A and a point a little bit away from A, H away from A, in fact, because of this A plus H. So, for example, we're at some point A, and we want to use another point like A plus H, and eventually we're going to make H close to 0, so those are as close together as possible. We would be using a situation like this. These 2 points, neither one known to us, to set up our slope equation, and we find that 4.9a plus h squared minus 4.9a squared divided by h. What does that equation look like? Think about it. We're going to talk about it in class tomorrow.